Hello everyone, this is the last video of chapter 4 of the lecture notes, and we're going to solve exercise 43 of the lecture notes, which is an application of the El Gamal cryptosystem. So as always, when we're doing exercises, please pause the video, try to do the exercise on your own, spend as much time as necessary, perhaps 1 day, 2 days if you're blocked, and when you are convinced that you're stuck, or when you have managed to solve the exercise, please come back and look at the video to see if what you have done is correct. Okay, so this is a typical exercise in which we have two people involved, Alexandre and Bernard, which are using the El Gamal cryptosystem. They have a public domain, so here we are given all the information known to Alexandre, and when we're doing El Gamal cryptosystems, we have several informations. First, the public domain, so that is the cyclic group in which Alexandre and Bernard have agreed to work. And we have the public and private key of Alexandre, and since this is the information known to Alexandre, we also know the public key of Bernard, but we do not know the private key of Bernard. Okay, good. So as you see, in this typical exercise, first you're asked to check the data, then to cipher some message, then to decipher some message. Okay, and then the last question, to find the private key, because in this case, since this exercise is quite simple, one is able to find the private key. Good. So let's start with question 1, where we have to check all the data. So what do we mean by checking all the data? Well, basically there are two things to check. First, we have to check here whether this is indeed a cyclic group. Okay. Cyclic group. Is this a cyclic group? And is this 7 here a generator or not of the group? So this is the second question, right? Is this a generator of the group? And then the second thing that you need to check is whether the relation between the public and private key is correct. Okay, the relation here between EA and DA. So let's start with checking what happens with the public domain. We need to check. So 1, let us check that 7 is indeed a generator. Is indeed a generator. Generator of the group. So the group we are given is F23 star, and when it's not specified, it means we're using multiplication. So I recall you that this notation is the same as saying that we are using, we're working modulo 23, so Z over 23Z, and that we're using multiplication, okay? The star to say that we are not taking 0, otherwise not form a group. All right, so how do we know if 7 is a generator? So we need to find the order of 7. Okay, so this is the same as, let us find the order of 7. Order of 7, the best technique to use the order of 7 is using Euler's theorem, right? Euler's theorem, which tells us that the possible orders must be the divisors of the number of elements here. So since we're working modulo 23 and we're taking the 0 out, there are 22 elements, and the possible orders are the divisors of 22, right? The divisors of 22, well, there's not so many, just 1, 2, 11, or 22, okay? So our goal when we're trying to find if 7 is a generator is to check that the first power for which 7 to that power is equal to 1 is 22. Okay, so we just need to compute all the different powers of 7. So of course, 7 to the power 1 is not 1. 7 to the power 2 is 49. Modulo 23, that's 3. So that's not 1 as well. And if you compute with your computer or whatever other means that you want, 7 to the power 11, you will see that this is equal to 22, which is not 1, modulo 23, right? So And the last one is 7 to the power 22, but this one you're sure that it's equal to 1 because of Euler's theorem, right? It says any number to the power 22 is also Fermat's little theorem is going to be equal. So therefore you see that the order, so order of 7 is indeed 22, which is correct. Okay, so that means that 7 is a generator of the group. Okay, so the public data is correct, the public domain is correct. The second thing that we need to check, so that was the first one. Second thing that we need to check is the relation between the public and private key, between public and private key. Okay, so the relation should be that EA is equal to the generator of the group to the power DA, right? So we just need to compute it, and we have 7, so the generator of the group that we chose was 7. The private key here is given is 10, so if we compute 7 to the power 10 modulo 23, well, you'll realize that this is indeed equal to 13. Okay, so we do have the correct relation between the public and private key of Alexandre. Okay, so these are the two things that you had to check in the first question. Good. So now let us go to second question of the exercise. So in the second question of the exercise, Alexandre wishes to send the plain text x equals 12 to Bernard, and we're asking to we are asked to cipher the message. Okay, so when we're doing El Gamal, you have to remember that there are two steps in ciphering a message. The first step is the generation of a disposable key, right? Generation of a disposable key. And the second step is ciphering the message, right? And ciphering, okay? So here we are told that by whatever means Alexandre chooses to use as a private disposable key k equals 7, okay? And therefore the public key that is going to be published is r equal to j to the power k here. So you just need to compute 7 to the power 7 modulo 23, and if you do the computation, you'll see that this is equal to 5. Okay? That's the first part. The second part, the enciphering transformation. So you just need to remember the formula of how this works. So if the enciphering message y is going to be equal to the plain text x multiplied by the, so we are sending a message to Bernard. Therefore, we are going to use the public key of Bernard, right? EB, and we're going to use the disposable key K. Okay, so that's how it works. If we're sending to Bernard, remember that we have to use the enciphering key of Bernard, right? Okay, so we just now need to make the computation, knowing that x is 12 here, and that the enciphering key of Bernard is 15, and k is 7. So you just need to make this computation, modulo 23, and if you make the computation, you'll see that you find 17. Okay, so once you have these two, the message received by Bernard, received by Bernard is in total the disposable key 5 and the ciphered message 17. Okay. Good. Good. So let's move to the third question. Now it's a question about deciphering a message. Okay, so Alexandre receives the message. So what is the message that Alexandre receives? 2011, receives the message 2011, okay? And there are always two parts in the message, right? The first part of the message is the disposable public key here. Public key. And the second part here is the ciphered message, right? Okay. So if Alexandre is going to decipher the message, he is going to use its own deciphering key, right? To decipher, you have to use A's deciphering keys, right? Deciphering key, which is secret and only known to A. So the calculation that we need to do is X is equal to the ciphertext Y multiplied by the disposable key R to the power the A, the deciphering key of A, and this to the power -1. Okay, so in fact the computation is 11 multiplied by 20 to the power, so the A was here 10, and the whole thing to the power -1, okay? So you can start maybe computing R to the power -1. We have 20 to the power 10, that is equal to 8, okay? And then you have to find the inverse of 8. Luckily, this time is very easy. We don't even need to use the extended Euclidean algorithm to do this because modulo 23 is quite obvious. 8 times 3 is 24, so that's equal to 1 modulo 23. Therefore, the inverse of 8 is 3, okay? So X is equal to 11 times 3, which is 33. Therefore, 10 modulus 23, okay? So the plain text, the original message that was sent by, was meant to send by B was 10, okay? Good. And now let's finish the exercise with question 4. And question 4 of the exercise here, it was in the simple example, the private key is not so secret. Find it, okay? So normally remember that the DB is protected, the secret of DB is protected by the difficulty to solve the discrete logarithm problem, okay? So remember that DB is equal to the logarithm in base G, so in base G 7 of EB, right? So the question we are asking here is 7 to which power will give 15 as a result, okay? So 15 is 7 to which power? Well, here there is not really a method, a smart method to do this, but since the group that we have chosen is quite simple, we can just compute all powers of 7 and see which one will produce as a result 15, okay? So we just do this, we just take n and we'll compute all powers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. Let's see if that's enough. All powers of 7, and we'll stop whenever we see 15 appearing in the table, okay? And that will give us the private key. Okay, so 7 to the power 1 is of course 7. 7 to the power 2, we already saw, is equal to 3. And then now you use a computer to do this. Well, 7 to the power 3 is 3 times 7, 21. So that's easy to do. 7 to the power 4 is 21 times 7. So you can either use a computer or use the fact that 21 is -2. So it's -14. -14 is 9. And so on, right? So I can just tell you the results here. So 7, 3, 21, 9. Then to the power 5 is 17. So we will stop whenever we see that 15 appears in the list, right? Then we continue. Here it's 4 to the power 7. It's 5 to the power 8 is 12. To the power 9 is 15. So here is when 15 appears. So we don't need to go any further. here we have on the bottom, the public key, right, EEB, and on the top, the private key of Bernard, DB, all right? So DB is equal to 9. Okay, so of course here it's possible to find DB because we have a very small group, but if we had chosen instead of working modulo 23, we would have chosen a huge number, then this method of finding the private key would be hopeless because there are too many calculations to do.